All right. I just briefly want to talk about analog measurements using things like a ruler or a meter with a needle. So let me get an example of that. So or a meter with a needle like this, or a triple beam balance also would be an example. So. Triple beam balance like this. So how do we determine the uncertainty on analog devices like that? So many people are taught a rule that it's just half a division. I was actually at some point taught a tenth of a division, and the reality of it is somewhere between the two, to be honest. So just as a little activity to show that no one rule really works, what we're going to, for all cases, what I'm going to do is I'm going to take this meter stick and I'm going to draw a line at both sides. So here's one end, and here's the other end. So now if this is my measuring device and that's 1 unit, and I just draw a line somewhere in the middle. Obviously I can tell better than a half a unit that this is near the middle. It looks like it's maybe slightly over the half of a unit if we're starting from the left. So maybe it's closer to 0.6 than 0.5, but I would call this 0.5 plus or minus 0.1. Now what we can do is, if I come back, and I'm going to try to not look at the actual exact measurement, but I'm just going to draw lines every 10 centimeters. And these are not very straight lines, but that's okay. So now, those are every 10 centimeters. We can tell that I was pretty close to correct. This is 1, 2, 3, 4, 5. So it's 5, and then I would say that's 0.4 of another division. So I'd say it's 54 centimeters plus or minus maybe a centimeter. So now if I come in with the actual meter stick, I can see that it's 54.3-ish centimeters. And I'm not even measuring past a tenth of a centimeter, which is the smallest division on here. But anyway, as you can see, here I accurately could tell that this was 4/10 of this division. So with a device, if my measuring device is like this, where there's a lot of space between the divisions, and whatever I'm measuring is very small compared to the divisions, for something smaller you may need a magnifying glass or something, but you can tell better than a half a division in some cases. In other cases, if your divisions are very large compared to the space between them, like they are on a meter stick, or the object is very fat compared to what you're trying to measure. So, if I'm trying to measure the center of this line, the line itself is I don't know, half a centimeter wide. So that can make it harder to estimate accurately a tenth of a division or something like that. So in that case, if I'm using the actual meter stick to measure this, my lines are not super thin. So yeah, I might say 54.35 centimeters, because I think it's halfway between 3 and 4 on the millimeter scale. So I hope that just shows that, there is no one right and wrong rule that always works for analog instruments. Um, Metrologists who study these things could, go on and on for a long time about, whether you should estimate to a tenth or a half, depending on the specific instrument. Another thing is certain instruments will actually tell you what they should or should not be measured, or what accuracy you should be measuring to with them. So for example, on this, I don't know if you'll be able to see it on there, but over here, it says class 2.5. And you can look that up online, and that will tell you how accurately you're supposed to measure that analog meter. But there is no one hard, fast rule that will just work for everything. And so it's best to just be honest. You can also, you might be wondering, why does it matter if I, over or underestimate the error? But if you're trying to actually come out with a precise and accurate result and determine, whether something agrees with previous measurements or a theory or something like that, you need to have an accurate uncertainty. If you overestimate your uncertainty, then maybe if you estimated it correctly, you would have agreed or disagreed. Well, okay, if you're overestimating, you're more likely to agree even when your results may not agree with something. So let's say, I'm measuring gravity like we're going to do today, and I overestimate my uncertainty. Then I may have a very bad result due to, some error that I've made. But I won't see that because my uncertainty is large. So it says that I agree with the standard measurement, even though in reality my experiment shouldn't have agreed because of a mistake or something. Or maybe, you go to Mars and you measure gravity and you do a bad job and you come out with that it's the same as Earth. I don't know. But if you underestimate your uncertainty, then what will happen is, maybe you do a good job on the experiment today and you come up with something close to the actual gravitational acceleration, but because your uncertainty is underestimated, it doesn't agree within your uncertainty. So, it looks like you did a bad job even though you didn't, because you've underestimated your error.